All right. Hello there, everyone. This is Jesse Johnson from Tutoring with a Twist. And I just wanted to make a video, and I was going to see just how quickly I could explain everything that you need to know to understand trigonometry at the upper high school level. Um, and of course, that's going to begin fairly simple, and it's going to get a little bit trickier as it goes. So let's say we've got a right triangle. Right, that's going to be our place that we start. Um, and as you might well know, the right triangle has this interesting property, which we'll call the Pythagorean theorem, which is that if you square these two sides, the two not diagonal sides, that'll also be the square of this side here. So for instance, if I have this side of length 4 and this side of length 3, then I can find out the length of this side here, right, with a fair amount of ease. That's going to be 3 squared plus 4 squared equals c squared. We'll use c as the length of the hypotenuse, which is that diagonal side, the side opposite the right angle. 3 squared is 9, 4 squared is 16, equals c squared. 9 plus 16 is 25, equals c squared. And so you can take the square root of both sides and get that c equals 5, right? So if we have a right triangle and we know 2 of the side lengths, we can find out the third for free just by using the Pythagorean theorem, right? And that's going to be vastly, vastly useful for developing a whole bunch of other things, right? And even just on its own, it's pretty exciting, I would say. This triangle in particular is going to be one that's going to pop up a lot. This 3, 4, 5 triangle is, I would say, far and away the most famous, 3 lengths of the sides of a triangle to exist. But it's not just that, right? Even before we start on the, that SOHCAHTOA or anything like that, we've got another fun rule that we have, which is that given any specific triangle, right? Let's just go ahead and make one up. Right, there's just a triangle I made up out of nowhere. I know that the 3 angles have to add up to 180 degrees. So this should all be reviewed for you if you're watching this to sort of prepare for high school level math or early college trigonometry. You should remember that the 3 angles of a triangle are all going to add up to 180, right? So for example, if this angle is, let's say, 40, and this angle here is, I don't know, let's say 60, right? And that would mean that this angle here would have to be 80, so that the 3 angles all add up to 180. Right? That said, this is definitely not enough to know everything about every triangle, right? So if we've got a right angle triangle, if we know 2 of the sides, we can find the third. And if we know 2 of the angles, we can find the third. But there's not at first, not apparently, there doesn't seem to be any such luck for if we say know 1 angle, we'll call that theta, right? And we know a side, and we want to figure out, say, the length of this side, right? So let's say, for example, that I throw a triangle at you, right? And it's got a 30-degree angle here, for instance. If I asked you, how long is, say, this side here? You would probably say that you have no idea, and there's absolutely no way for you to be able to tell. And you'd be right, because after all, this 30 angles is well and good. We know the shape of the triangle, but it could potentially be very, very big, or it could potentially be very, very small, as long as the angle is the same. Fortunately, I'm having a little bit of difficulty, playing with it like that. But you can imagine, right, that you could have a maybe a several mile across triangle, would be definitely differently from a different size, from say a several inch across triangle. But they might both have this 30-degree angle, right? So it seems like we're out of luck. But in this specific case, we actually have a huge windfall coming to us, because we know that if this triangle has a 30-degree angle here, then that means that this side here, across from that angle, sorry, did I say that side? I meant to say that side there should have exactly half the length of that side there. Am I right about that? I'm so sorry, getting all mixed up. I was right the first time. That side there will have half the length of the hypotenuse, right? Which is very, very exciting. So what we might do is we might say like, okay, well, if you've got 30 degrees, right, then the ratio of what we'll say called the opposite to the hypotenuse is going to have a certain value, right? Which is all very, very nice, right? And so people found this and discovered it and said, oh, that's very amazing. That's pretty incredible. Until later on, it turned out, what if you had a 45-degree triangle, right? We can add that to our little table here. So we'll call this side theta, right? And if it's 45 degrees, then we figured out that it's square root 2 over 2. And if it's 60 degrees, then it's another number. And if it's 70 degrees, it's another number. And onwards, right? And we just kept making all of these big tables. They're in these old musty reference books. You can still find them if you search for them. But the idea is that if you know what the angle is, you can figure out the ratio between the opposite and the hypotenuse, right? If you know the angle, you know the shape, and then you can just look it up to figure out what that is, right? And eventually people thought to themselves, we really need a name for whatever is this ratio on the opposite side from the angle that we're talking about. And they did come up with a name for it. They call it the sine. Right? So for example, in this case, the sine of 45 degrees is the square root of 2 over 2, right? So we'll establish the sine, which is going to be the opposite of hypotenuse. We're also going to establish the cosine and the tangent. This is probably a word you're familiar with, is SOHCAHTOA. SOHCAHTOA. So let's see if we can piece together what this stands for. I've got some practice problems here, but before I'm going to shrink them down, right? Get those out of the way. Let's piece together what this whole SOHCAHTOA thing means. Well, sine of theta, by definition, by the way we define it, is going to be equal to the opposite over the hypotenuse. Likewise, the cosine, which we'll abbreviate to COS of theta, right? It's not cos, it's cosine. COS of theta is going to be equal to the adjacent over the hypotenuse. And then, of course, the tangent, abbreviated TAN, tangent of theta equals the opposite over the adjacent, right? So these are the ratios that we have here, right? We can use these ratios to discuss the side lengths of triangles where we maybe, don't know much, right? So let's say that I kind of gave the gun away by showing that number earlier. But let's say we've got something like this, right? This 60-degree triangle, 10 length of 10 on that hypotenuse there. How do you find this side length right there, that one off to the side? Well, which of these equations contains the things that we're talking about? Looks like we're talking about the opposite, because we're talking about that thing on the opposite side of that angle, as well as the hypotenuse. So we might want the sine of theta, right, which has the opposite in the hypotenuse, right? So we'll set up our equation just like this, just so. We can say sine of 60 equals the opposite, which is just x, over the hypotenuse, which is 10. Right? Solving this for x, we would multiply both sides by 10, and we would have that x equals 10 times the sine of 60. You can go ahead and get your calculator out. You can plug in 60, take the sine of that, multiply it by 10, right? And we will get that x equals about 8.66. Right? So if I had a 5 up there earlier, that was a lie. What I meant to say was 8.66. Let's do another sort of practice like this, right? This time we'll set up a triangle kind of like this. So just as a reminder, you're not always going to have triangles kind of appearing to you in the same orientation every single time. Let's see if we can I'll get rid of this. We don't need it anymore. Let's see if we can suss out what x here would have to be. So it looks like we're not dealing with the opposite side. We're dealing with the adjacent here, as well as the hypotenuse, right? Adjacent hypotenuse, it sounds like we're going to want the equation for the cosine. Right? So we'll set that up. The cosine of our angle, which is 45, equals the adjacent, which is 7, over the hypotenuse, which is x. Okay. Now we can do a little shuffling around to solve this for x. One thing we might do is we might take x and move it over onto the other side here, right? And we might also, just by multiplying both sides by x. And we might also take the cosine, push it over onto the other side there. And what do we end up with? We'll have that x equals 7 over the cosine of 45 degrees. Again, I'm going to go ahead and plug this into my calculator, just out of curiosity to see what we end up with. I've got about 10, just under 10, right? 9.899. So we might even round that up to 9.9. X equals 9.9. And that's, for the most part, everything that you'll have to do in sort of basic trigonometry, right? This is the whole idea here, right? There are a couple of other trig functions that we might want to look at. I'll skip the word problems for a bit. Let's talk about this, right? So if we've got, say, sine, cosine, and tangent, that's all well and good, right? But we're also going to want to talk about their inverses. So what is an inverse? You might recall an inverse is something that undoes something. So for instance, the inverse of multiplication is division, and the inverse of addition is subtraction. Well, there's not really any fancier name for it, but the inverse of the sine function is the inverse sine. We'll do it sine and then a little tiny -1 up at the top. And it's going to do exactly what it sounds like. Instead of plugging theta in to get opposite over hypotenuse, you plug in that opposite over hypotenuse to get theta, right? So for instance, let's say that you're trying to figure out this angle here based off of the side length that we've got there, right? Well, one thing I might do is I might say, well, look at this. I've got the opposite there. It's opposite my angle. And I've also got the hypotenuse, which I know is hypotenuse. It's opposite that right angle. So I can set up the inverse sine of the opposite over hypotenuse to get my theta, right? Of course, the opposite is going to be 5. The hypotenuse is 10. So this is the inverse sine of 1/2. Yeah. And of course, if you work that out, my drawing here is maybe not quite to scale. You're going to get that theta, or I guess in this case, x is equal to 30 degrees. Okay, let's try this again. Let's do another fun practice problem here. So if we're working on, let's say that we want to know the angle of that famous 3-4-5 triangle that we were talking about before. Well, we might say, let's find the inverse tangent, right? Not the tan -1, but the inverse tangent is the exact phrase we're going to use, of the opposite over adjacent. That's going to be our theta. That's going to be x in this case. Right? The opposite is 3. The adjacent is 4. So we'll set that up, 3 over 4. And once again, I'll grab my calculator, just figure that out real quick. 3 divided by 4. Take the inverse tangent of that. It looks like I've got about 36, 37 degrees. So 36.7 degrees is what we get for x. So the reason that we spend so much time absolutely drilling trigonometry into the heads of students is because it can solve a lot of very practical problems. For instance, let's say you might imagine that you live in a period of time where technology is not quite what it is today, and you want to find the height of some building, right? So here's this the skyscraper. So maybe technology is more advanced than I give it credit, and you want to find the height of it just as a person standing here on the road looking out at it. Well, one thing that you might do is you might say, well, what if I can construct a right-angled triangle, right? If I can construct a right-angled triangle, that'll give me just about all the information I need to figure out the height of this tower here. So here's your eyes, beam them up, right? Look up there and there, right? So we'll call this angle here, I'll label it X, but we'll call that the angle of inclination, right? That's the angle in which you kind of have to look up to see something. Right? The opposite of that is going to be the angle of depression if it's going down. So let's say that we've pasted out, and let's say that we know that we're standing 50 meters away from this building here, right? Let's say that we've very careful and we measure and we know that we're looking up at let's say a 20-degree angle up at this building. This might wind up being a very short building, but we'll find out, won't we? So we're trying to find X for the height. You might also write H, doesn't matter much. So what equation we're going to use, we'll probably going to want to use the tangent, right? Because we've got the adjacent, we are looking for the opposite. That's exactly what the tangent was made for. So we'll say that the tangent of 50 equals TOA, opposite over adjacent, equals X over 50. Did I say tangent of 50? I'm so sorry. It's hard to do it all in one take. Tangent of 20. There we go, that's better. So in this case, how do we solve for X? Well, it's simple. We'll just multiply both sides by 50. Move that over there. I'll go ahead and use my calculator to evaluate that. 20, find the tangent, and multiply that number that you get by 50. And there we go. I've got 18 meters, which I think is a reasonable height for a building, 18.19. Now, there's one small caveat to this, which is you're also a person with a certain height of your own. Let's say that you might be, I don't know, 1.7 meters tall, right? If we want to find the overall height of this building, we'll have to say the height up from our eyes plus that 1.7 meters. So in this case, the overall height of the entire building is going to be 19.89 meters, about 19.9 meters, just shy of 20-meter tall building, right? Let's see if we can solve a problem that's just a touch trickier here. So for instance, let's say that you are trying to find the height of this very, very tall tree, right? It's a absolutely massive tree, and you're trying to find the height of it. So you stand over here. You don't know how far away it is. It's maybe it's on the other side of a ravine or something. It's a very a very visually exciting hike that you're going on. But maybe here's what you do know. You know that if you're standing there and you look up at the tree, right? You know that that is let's call that a 50-degree angle up at the tree, right? Dot, 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 dot. You take, let's say, 20 steps back, for instance, and you have another look, but now you're only looking 30 degrees up. 50 degrees, 30 degrees. So here's the question, is what is the height of this tree here? Right? How can we find the overall height of the entire tree? Well, one thing we might do is we might construct a right triangle just like that, right? And we've got h there is an unknown, and d, distance, is an unknown. But we can, we can set up the tangent, sort of figure out the ratio, right? So we know that for one thing, tangent of 50 equal to opposite over adjacent, remember? So that's going to be equal to height over whatever that distance was. And while we're at it, we can also set up I'll do it in red so it's easier to see. We'll set up a second larger triangle, right, from our slightly further distance away, right? So in addition to the tangent of 50 equaling the height over the distance, we also get to know that the tangent of 30 equals the height over distance plus 20. And we can certainly do plenty to solve for this. So for one thing, we can solve both equations for height, which is the thing that we're trying to find in the first place. So it's not a terrible idea to solve for height. Now we've got this equation here. If you know much about solving systems of equations, this maybe shouldn't be too big of a challenge for you. If you're a little bit rusty in terms of your abilities to solve systems of equations, not to worry. We can solve it anyway. I might point out that both of these are equal to height, right? Which means that we can simply say that we'll have this equation here. I'll go ahead and put brackets around that. Plus 20. Right. Maybe we'll divide both sides by tangent of 50. Right. Okay, getting fairly close. And we might also, let's see, what could we do now? We could also multiply out that, factor it out. Okay, so we would get, here, let's adjust this. So b times tangent 30 over tangent 50 plus 20 times tangent 30 over tangent 50. That sounds very scary, very complicated, but it's really its bark is worse than its bite. No pun intended, since we're talking about trees. The tangent of 30 is equal to 0.577. So I replace tangent of 30 with 0.577, right? The tangent of 50 is equal to 1.91 or 1.192, we'll say. Which means that the tangent of 30 over the tangent of 50 is going to be equal to, it looks like about 0.484. Right? Okay, we'll multiply that by 20 times 20, and we'll get 9.681. Right. We're also going to go ahead and, no reason not to, might as well put it in there as well. So that 0.484 times 0.484, right? And then we'll subtract this thing from both sides. This is 1d, so 1 minus that whole thing that we just found. 1 minus 0.484 is equal to 0.516. Right, so we're subtracting 0.484d from both sides to get 0.586d equal to that number there. Did I say 586? Sorry, just look back to my calculator. Somehow misremembered that. The final thing that we'll do is we'll divide both sides with that 516, and we'll get d equals 9.681 over 0.516. We can go ahead. I'll calculate that lightning speed right now. There we go. It looks like it's about 18. So this is probably an 18-meter tree. Or sorry, it is the original distance would have been 18 meters, right? Oh, sorry, getting distracted. 18.76. Right? So that's our d, right? That's our distance away. Right? 18.76, right? I know this seems like a whole lot of rigmarole, but we're almost there. Now we would just say that the tangent of 50 is equal to the opposite over adjacent, equal to the height over 18.76. We can multiply both sides by 18.76. So 50, take the tangent, times 18.76. Ta-da, we've got that the height is equal to 22.36. There's the height of this beautiful tree. Okay, so this is all well and good, right? You might be wondering, can I take this to the next level, right? This is all cool, but this is all stuff that I might have done, you know, in earlier grades. Well, there's a couple of things that we can do. First of all, you might be tempted to talk about some of the more complex of the trig ratios. Right? I'll go ahead and forgot to make a page for it, so I'll make that now. These are very, I said more complex. That was a lie. Some of the other trig functions, you might have heard of them. So for example, we have the sine of theta is equal to the opposite over hypotenuse, right? Well, the cosecant, CSC, of theta is equal to the hypotenuse over the opposite. So you might notice something interesting, which is simply that the cosecant is equal to 1 over the sine of theta. Right? So this is maybe why we don't talk about the cosecant so much, is because you can figure it out entirely just using your knowledge of sine. It's exactly just 1 over the sine. Likewise, in the same way that we've got the cosine of theta equal to the adjacent over the hypotenuse, we'll also have the secant, right, SEC of theta is going to be equal to the hypotenuse over the adjacent, right? Which, of course, likewise is just 1 over cosine. And then to complete the pattern of tangent of theta equals opposite over adjacent, whereas adjacent over opposite equals the cotangent of theta. Again, just 1 over the tangent. So there's nothing too terribly surprising here. Now that's regular old triangle trigonometry, where it gets the name from. We also have circle trigonometry to talk about. I think I might call this video a video here, and then make a quick follow-up video that explains that. So hopefully you'll join me for that, and I hope to see you soon.